Okay, good point. It's only please don't turn into a ghost instability. Okay, just decay. I mean, okay. All right. So then I evaluated this ratio here. You see, I took the coefficient and divided by ng1 square, and we found that. So then he finds this relation. And okay, it's here. And they said that's the standard again relation for CS square, because we know that the CS square is, we said, is P dot divided by rho dot. Okay. Right. And P is n d rho over dn at constant entropy minus rho. So when I do the P dot, when I do dp will be, right, so dp will be dp over dn at constant n times n dot plus dp over ds constant s, constant n, s dot. But this one is 0. What happened? Yes, P dot. Thank you very much. At least you didn't decouple. That was good. Thank you very much. I'm very helpful doing it. Very good. I'm not kidding, eh? I really mean it. Okay, so P dot, so then P dot, this will be dp over dn at constant s divided by rho dot, and rho dot will be d rho over dn n dot. Okay, for the same reason here. So then n dot will simplify, and we'll get dp over dn at constant s over d rho over dn at constant s. Now, P, as I said before, was n d rho over dn at constant s minus rho. So if I do the dp over, so this was dp, huh? dp over d rho of constant n. So this is constant, we'll get n d rho square over dn at square a constant s plus d rho over dn a constant s minus d rho over dn constant s. These two simplify, and finally we get n d rho over dn square a constant s divided by d rho over dn at constant s. So, and this is exactly what's written here. You see that this is n, the second derivative, partial second derivative of rho with respect to n, divided by d rho over dn. Okay, so indeed we saw that the CS square is actually indeed a speed of propagation, and it's the speed of propagation of these modes for the superhorizon scale. So again, okay, yes, I had to say something here. I said CS square must be negative, okay? And I told you it must be negative, otherwise omega becomes complex. And if you have omega ei omega t, omega will plus or minus I of something. So if you see square negative, this will be plus or minus modulus of CS times k t. Okay?
Here you are taking delta m as of this form, no? E raised to I omega t.
Yes. Okay. And remember there was plus, say, minus I kx. Okay, this is really wave, plane wave.
I can't see, is it rho dot upon p dot, is it p dot upon rho dot?
This is p dot divided by rho dot. So this is dp over dn, d rho over dn.
That means here you are considering the particular form of rho.
Yeah. So, what? So I am no.
Not here in this form.
Over there.
Yeah.
No. So I first assume that the time. So the solution was similar to an exponential e to the I omega t, and I was finding that it was true when omega was CSK, p divided by a. Okay, and I'm saying that if c squared is negative, then we will have something like sorry, this would be I, and so we'll have like one mode which is growing and the other mode which is actually decaying. So, but there is a growing mode. Okay, so there is an instability, okay, which is not the Gauss instability. Some people call it gradient instability. Some people call it Laplacian instability. Anyhow, what is this instability? The instability is, okay, growing mode, okay. And when we say we have an instability in the system, we have to make sure to have an idea what is the time or the typical scale of time for this instability. And point here, the typical scale of time will be inverse omega, right? So there will be the typical period of the wave. So because of that, and we assumed omega was very large, we would expect this time of instability to be very, very small compared to the time of evolution of the universe. So if you have such an instability, the universe becomes non-homogeneous or isotropic in a very, very short time. When I say short time, much smaller than the evolution of the universe, actually. So this would be too fast instability, so that we cannot allow this instability to. So the Friedel Hamilton worker will be a bad approximation at some point, but in a time scale which is too short compared to the lifetime of the universe.
That means you don't allow
C squared to be negative.
To propagate in a large scale.
Yes, exactly.
Yeah.
So in order for that to be not the case, we had to set this quantity to be positive. Okay, but then because c squared will be positive, then omega will be real. So e to the I omega t will be purely a wave.
We also don't take e to the power minus I omega t to begin with. So plus minus I omega t both are possible.
Yeah, I mean, yeah. If we put minus here, and then but still you have that omega is plus or minus something. So whatever.
It has to be real, omega.
Omega must be real. As soon as you have a imaginary part, then one of the modes will be decaying, the other one will be exploding, actually.
So you want your perturbation in waveform, so you are taking this form of delta M, no? E raised to I omega t minus ik.
Yeah, we saw that this was a good solution, because omega was independent of k, just a function of time times k. This was an approximate solution. So then, if there is an instability there, we expect that instability to really occur in the universe. Okay, so this is. But remember that any instability, even at present, one should have an understanding of what is the time of instability for that object. Okay, now let me study what is this d term. Okay? And the d term was this one, which is a bit, not so clear. And we said that, remember that the no-gauss condition must set d to be positive. Remember that yesterday we integrated out. We'll get 1 divided by d in the denominator. Do I have to do the calculations again? Okay, let me do. So suppose that c is equal to 0. I have only those two terms there. And suppose d is different from 0. So suppose d is different from 0, then the equation for this term will be 2ds plus n0 delta t dot equal to 0. Okay, then I solve for delta s. Okay, delta s will be equal to n0 divided by 2d times delta theta dot. Then I replace into this thing here. I will get minus d times n0 square divided by d square delta theta square plus n0 plus n0, and then I had to replace delta theta dot and delta s, which is n0 times 2d. Sorry, there was a 2, no? So this there is a 4 here. 2d times delta theta. Okay? So I have 2d minus 4d. The whole thing becomes n0 square divided by 4d times delta theta dot square. So the no-gauss condition imposes d to be positive. Okay? So when this thing happens, we have delta theta is only kinetic term. Okay? Then delta rho will have a kinetic term and mass and the Laplacian term. And then we have this kind of thing here. So d must be positive. Positive or equal to 0 at most. What happens if okay. Yes, I didn't say this. What happens if d is equal to 0? Then this term is 0. And what happens that this becomes, both become Lagrange multiplier of the second kind. But we cannot integrate their own equation. We cannot touch that Lagrange. Okay? And that Lagrangian will have no Gauss condition. Okay, when d equal to 0, we cannot set delta theta to be 0. Okay, that was yesterday. We cannot. So we had to leave it like that. We had to. Well, if d is equal to 0, we leave this one as it is, nothing else. We cannot touch it anymore. But the point is that there will be like trivial things, because delta s will set delta theta to be constant, and delta theta will set delta s to be constant. Purely initial conditions, no dynamics on that. Right. And remember that this is like a magnetic kind of interaction. If this is 0, this is magnetic interaction. And I said when you write down the Hamiltonian, they will disappear. The term. Okay. So anyhow, so let's study now what. Suppose d is different from 0, and see what it is. It is that one. So for a barotropic equation of state, it doesn't vanish in general. So let's see what it is. I tell you the answer. Well, so see what I've done here in these two steps. I say, okay, I know the temperature is this. So I tell you the philosophy before doing before doing the calculations. I said Maybe that is related to some thermodynamical quantity. So we know that d rho is equal to mu dn plus nt d rho ds. So this fixes t to be 1 divided by n d rho over ds at constant n, and mu to be d rho over dn at constant s. Okay? And then in the first line there, I put a Tt, which is just means temperature, actually. I just didn't want to call T because T was already defined in the code. So T as a function of Nn, and again, Nn is just another variable that stands for n. But if I put n, the monster object of the perturbation comes, OK? So just to keep it, this is just function n in thermodynamics. As constant, this is my definition of temperature. And pressure is n times the mu minus rho. OK? That's all what remember that P is equal to n d rho over dn constant s minus rho, which is mu n minus rho. OK, that's what I wrote in the second line. Now, what is that? So what is d? D is related to this quantity here. Somebody can guess what is? If you guess right, you are. Wow. Does anybody guess what is this? Okay. If you, I mean, it's important. To be honest, it would be important. I mean, unless you because those variables are not really much used in thermodynamics, but OK. So what is there, actually? Let me calculate this quantity here. Cp. Cp is the heat capacity, which is defined in the following way. We give heat to the system, and we say how the temperature changes with the Q at constant pressure. Now, delta Q is Tds divided by, sorry, then this one becomes ds divided by dt at constant pressure. OK? Right. Now, remember that we define the total entropy as n0 times s, because little s was the entropy per particle. N0 is a constant. So this is n0 times t ds over dt at constant pressure. OK? Now, it's a property of partial derivatives. This one is n0 t divided by dt over ds at constant pressure. So 1 over the derivative, keeping the same variable p constant. OK, that's kind of standard derivative kind of. OK, so let me try to find, because I know what is t is this object here, and p is this object here, and I want to study what is n0t dt ds at constant p. OK? All right. But I would like to express this one in terms of delta t over n, because my variable is n, actually. So, OK, so let's do it here. It's almost over. And this probably is one of the last calculations we are going to see, actually. OK, so let me see. So then let's suppose we have dt. Then we can write dt ds at constant p ds plus dt dp at constant s dp. I have not I've written nothing but the fact that t may depend on s and p. However, I do this. The s is one of my variables, so I don't touch this part. But I say, OK, dp is dp dn, constant s dn, plus dp over ds at the constant n ds. Again, I didn't say anything, but p can depend on ns. And of course, I didn't change this part because s is one of the two variables that I want. OK, so this one becomes dt over ds, a constant p, plus dp over ds, a constant n ds, plus dt over dp at constant s, dp over dn at constant s dn. Ah, yeah, that's right. So dt over dp at constant s. Yes. OK, so remember we want to look, so this is Cp. So we want to extract this parameter here. And you see that, what is this? Well, remember that dt is still equal to dt over dn, a constant s dn, plus dt over ds, a constant n ds. Again, here instead I say t is a function of ns. But then this thing must be equal to this, and this thing must be equal to that. OK, so then we find that dt dp at constant s is equal to dt dn at constant s divided by dp over dn at constant s. OK, so from this one equal to that, I get the dt over dp is this one divided by that one. And this is good because I know t is a function of ns, and I know p is a function of ns. That's exactly what I wanted, right? But still, this is not that one that I want here, but this one I will get it from here. Because this says that dt over, I want what did I want? I want this one, right? This is the thing that I want. So dt over ds at constant p, which is the thing that I needed to put it here, is equal to, this one must be equal to that, right? So this will be dt over ds at a constant n minus this object here, which is dp over ds at constant n, which is something that I know because p is a function of Sn, times dt over dp at constant s, which is this, which is also something that I know. So this will be dt over dn at constant s divided by dp over dn at constant s. OK? Then I know what is Cp in terms of n0t divided by this. And n0t, t is 1 divided by n d rho over d s at constant n. So I know now everything. I can write it. Because p itself is a function of rho given by the expression there. OK, so follow me. So this is what exactly. You don't have it. Follow me. OK. It was a bit hard to follow me without a monitor. OK, so then we have that this is temperature in terms of derivative of rho, and pressure in terms of derivative of rho. Okay, so then I need to find this one. And you see, I defined dt ds at constant p. This one here. Dt ds at constant p, I said it to be equal to dt over ds at constant n, which is this one, right? Because I am deriving with respect to S0, minus dp over ds at constant n, dt over dn at constant s, divided by dp over dn at constant s. That's what I wrote there. Okay? And then afterwards, I substitute my, first of all, this variable here, n, which is n0 divided by a cubed, which is my number density. And remember, this was the condition to have a barotropic. And then if I do this, I get this one. And then the coefficient d is actually equal to minus, is actually, so if you take this, the coefficient d minus this quantity, you get 0. So then d is nothing but n0 divided by 2 dt ds at constant p, which was 1 divided by Cp. Okay? This was n0 t dt ds at constant p. So this one is n0 divided by 2 times n0t divided by Cp. So t is positive. The no-Gauss condition said Cp is positive. Okay? Which makes sense, right? Thermodynamically, we know that Cp is positive. When you increase the heat, you also want to increase the entropy. You increase the temperature at constant pressure, you want to also increase the entropy of the system. Okay. Now, the last thing that I want to do, Steve, and this is wow, because this is rho plus p. Cosmological perturbation theory says, hold on a second, you want to avoid the ghost, rho plus p must be positive. Because, of course, the numerator is always positive. Rho is positive, A is positive, and 0 is the total number of particles positive. Everything is positive except this one. This could be negative. So amazingly, cosmological perturbation theory has given us rho plus p positive, which was a thermodynamical condition. And this thing is true for any fluid, any perfect fluid, I should say. This is really, for me, it's really wow. Because cosmological perturbation theory, you may say, what is the connection with thermodynamics? I'm not exactly sure what is the connection with thermodynamics. But somehow the no-Gauss condition has a thermodynamic interpretation. Okay, so the first condition, then the first no-Gauss condition is 0 over dn at the constant s must be positive, and this is mu. The chemical potential for a perfect fluid must be positive. Who says that? Cosmological perturbation theory for lambda CDM. So if I have a fluid for which p plus rho is negative, very well, then I get a ghost. It's better not to have. All right? So that's this is the first non-trivial condition that we got out of a cosmological perturbation theory. It's not really the final answer. Remember, the final answer should have a part of theory. This is part of the theory, right? Because now we got this condition out of the theory. At the beginning, we didn't have this condition to be imposed. But now we know it must be imposed. Okay, so this is, say, a theoretical result, which you may think, okay, but it's interesting, but on the other hand, dust is, remember that for dust, rho is equal to proportional to n. So d rho over dn is just m0. M0 positive. This is rather trivial because M0 is the mass of each fluid element. Okay? Bah, okay, for dust, this one. Okay, it's true, but all right. For radiation, what is it? Because mu, indeed, mu is rho plus p divided by n. So p is one third rho, right? So this is 4/3 rho divided by n. But also this case seems to be okay. I mean, rho is positive, n is positive, number density is positive. Rho, if you want, that's the condition for you know, rho must be positive. But you know, that's again quite trivial, to be honest. It's quite trivial because we know that rho is proportional to actually is equal to sigma t to the fourth. No, this is we know for dust this is actually the case. So we know that rho is positive from the beginning. So for known fluid, this is, I would say, but it's true. It's a theoretical condition, but it's a kind of trivial in a sense. Is it trivially satisfied? It is true. Now, there is another non-trivial thing that will come from this one. Because we have another Gauss condition. Okay? And the other Gauss condition, what does it tell us? Well, we have to see. But before we see it, you may say, why did you stop here? I mean, we know that delta S can be integrated out. Why didn't you just integrate out delta S and gave us the final results? See, N0, this is a constant, which is the number of particles. By the way, also let me say something. I need a piece of chalk. So when we write down, did I erase? Oh, I erase. No, okay. So this is the Lagrangian. Okay, the Lagrangian is this object here. Okay, that's the Lagrangian we have. Suppose we find the equations of motion for delta rho. Okay, yes, actually, let's do first, simple things first. Let's find the equations of motion for delta theta. When I do the equations of motion for delta theta, my Euler Lagrange equation, dl over the delta theta dot, is equal to dl over delta theta. This is 0. So we find that the derivative of this guy must be equal to 0, and we get that delta S dot equal to 0. Okay? So this means that delta S is not 0. Delta S is a function of k, which means in coordinate space is actually a function of x. But delta S does not have dynamics, so delta S will be equal to its initial condition.
Delta is equal to constant, no?
Yeah, remember that we are like in Fourier space. So this one can be a function of k, or k square, I should say. So when you do this anti-Fourier transform, this delta S will be function only of x, not of time. Okay? By the way, in some sense, we knew this one, because if you remember, the equation of motion for S on any background is this. So when I take the linear perturbation equation, I will get delta UA d alpha S background plus U alpha background times d alpha delta S equal to 0. But delta S is a constant of the background. So this goes away. And the UA is only non-zero for the 0 component. Okay? The space component is 0. So this one automatically says dt delta S equal to 0. It's not a surprise. I mean, once we integrate the Lagrangian multiplier in a correct way, then the equation we get must be completely consistent with the initial equation we had. OK, so delta S, then, whatever it is, will be only initial condition. Now, the other thing that I want to say is that when we find the Euler-Lagrange equation, by the way, let me put a 2 here. When we find the Euler-Lagrange equation for delta rho, this object here will be derivative with respect to time of A divided by k square delta rho divided by rho dot, okay, because I had twice this one, and with a minus, probably, because I had to do integration with parts, plus, actually, no. Let me, yes, let me use the Euler-Lagrange equation, d over dt. This one will be the dl over d delta rho divided by rho. So this will be, there will be a mass term, so which is something proportional to delta rho divided by rho, and this one, plus c delta S. Okay? So what happens then in this? So the dynamics of delta rho will fill this constant source, constant times background quantity. Okay? So its dynamics is almost independent because delta S is really purely just initial condition. Okay? The equation for motion for delta S will give us delta theta dot. We'll get minus 2d delta S plus n0 delta theta dot. And now we may have plus c delta rho divided by rho. So once we solve for delta rho divided by rho, we plug it here, and we can solve for delta theta dot, because delta S is constant again. Okay? Now, to solve it, we have now the solution. But life this time is easier than what we expect. Let's see why. Now, what I do this, okay, so, okay, right. Oops, already this level. Okay, I wrote C2S there, but let me wait for a second here. Okay. Oh, I didn't want to do it now. Okay, let me do it now. Okay. So notice the following thing. No, I want to do it later. Actually, let me cut and paste this one. Let me remove it. And let me put it be here. Okay. And this coefficient. Sorry, yeah? Okay, let me go back to the point where we are now. Let me save it. So we got this no-ghost condition, we do this, and now I say to Maple, okay, please, Maple, show me this term C, which is the term which is proportional to delta rho divided by rho. Right? Because you say you see this term is proportional to delta rho divided by rho squared. Instead, I say to Maple, no, I want the term which is linear in delta rho divided by rho. So then it will give me C, probably multiplied by delta S. In fact, I have delta S, and I have this object here. Okay? This is it looks complex, and now I call this object here const. Okay? Now, what is this const here? Notice that I took this quantity and divided by a cubed. Okay? And you get this. This is the partial derivative of rho with respect to S times the partial derivative of rho with respect to n minus this one plus this one. In your notes, in the notes that I wrote, when you look for barotropic fluids, you will see that the barotropic equation state d rho over ds, a constant rho equal to 0, corresponds in terms of ns exactly to this condition, equal to 0. Whoa. Again, something very non-trivial came out. It means that for a barotropic equation state, for a barotropic fluid, this term is 0 identically. And what happens in this case, the dynamics of delta rho completely decouples from the dynamics of delta theta and delta S. Okay? Now, this thing is actually, we will see that this is actually the case, actually. I will show you explicitly that this constraint automatically vanishes for a barotropic equation state. But you can check in your notes, this is exactly the quantity that I was giving you that must vanish when we have a barotropic fluid. In terms of, so that's the barotropic condition in terms of rho, when rho is a function of ns. Okay, now having said this, this is very nice. Why? By the way, we know that dust and radiation are barotropic fluids, right? So for gas and radiation, for dust and radiation, this term will vanish. This is something very good. The reason why this thing is very good is because now the dynamics of delta rho is completely independent of this delta S, right? So people in astronomy don't need to think about what was the primordial initial condition for delta S. Because if that C was different from 0, one had a free parameter in the dynamics of delta rho. That was delta S. But with barotropic fluid, that coupling is absent. So delta rho is only sourced by itself. So we need just to know what was delta rho initially and delta rho dot initially, without thinking of what could be the value of delta S at the beginning of time, or at the beginning of whatever, of the dust approximation or gas approximation. So this is a very good thing, actually. Now, suppose we don't have a barotropic fluid. Is it possible? Yes, it is. Very simple example I gave you also in the lectures is that an ideal gas is something which has temperature, but it's not dust. Now, that object there would mimic a warm dark matter. Because there is T. And ideal gas is supposed to be non-relativistic, so the temperature cannot be much larger than the mass of the constituents. So it must be warm. It's not hot, but it's warm dark matter. Now, if we have a warm dark matter, it means that most probably we would need an extra parameter to know what is the dynamics of delta rho. This extra parameter is also called as isocurvature mode. The reasons of this isocurvature mode actually coming from inflation, actually. But in this case will be, just means that delta rho itself is not sufficient to know its own dynamics. Now we know that a model we call dark matter model works well, at least as far as we know. So it's probably, not probably, it's a very good approximation actually to consider dust really barotropic, and this thing goes away. Okay? Then delta rho, people just need, people who do numerical simulations or fitting data just need the field delta rho, just need to know what is delta rho. Okay. Just need to know what is delta rho and its dynamics, forgetting about what is delta S. Okay? Now, when C is equal to 0, then the remaining part of the action becomes completely decoupled from phi, from delta rho divided by rho. And then it becomes exactly equal to the example I gave you yesterday. Exactly equal. So that example yesterday looked like a bit of what was this guy is giving us. I mean, it's really we found in cosmological theory. It's cosmological perturbation theory. That relates delta theta dot, which is related to temperature. Okay? Now, we need to look what happens to the D thing here, because this was 0 after all, C. We need to check what happens to D. Okay? So what I do here, okay, I say this is constraint. I know this is constraint. It's the barotropic fluid constraint. And I solve these constraints because I know that I impose now the fluid is barotropic. Okay? So since now on, I will work with a barotropic fluid. So C will be automatically equal to 0. And because C equal to 0, this constraint will be 0. So since I impose this one to be 0 for a barotropic fluid, I solve these constraints for the mixed derivative. Okay? And I solve for this mixed derivative. And I will have that this d12 rho is actually this, is given by this solution, by which I found by solving this one with respect to this variable here. Okay, and then I impose this one into my action, and the action now becomes the following. I have my Gauss condition. I have my delta rho squared term, which I would call mass term. And then you see I have the term in delta, I have D, and D didn't vanish. Okay? First thing, we see that for barotropic fluid, D remains in general. And we have this field here. Okay? Now, yesterday we saw that when we have this thing, B must be positive. Remember, this was the no-Gauss condition coming from this thing. If you remember, B must be positive. That means that D must be positive. So we have another thermodynamical thing coming from linear perturbation theory in cosmology. If I think about this, I really like this, because it didn't need to be the case. How can cosmological perturbation theory is telling me thermodynamics? But now we saw that this thing is actually positive. And you know, the first time, it was years ago, the first time I saw this thing, I said, what is this condition? What is the physical meaning of this condition? Because this is complicated. You see, I have the second derivative of rho with respect to the entropy. So what's this? And this must be positive. I said, this is a new condition that we have in thermodynamics that was not found before. I was really excited about it. And I had to see what is the meaning of that. Okay, but before talking about the meaning of that thermodynamical object, which unfortunately it's not a new thing, I will tell you already, but it's something that we know it should happen in thermodynamics, okay? So before we go there, let me discuss now, okay, now I remove this term. This term doesn't exist anymore. Now, this is the Lagrangian. Forget about this part for a second of the Lagrangian. Let me discuss delta rho divided by rho, which at the end it's my physical field, which decoupled from the other fields, and is the one that I want to measure in my calculations. All right. So if you see this Lagrangian here, we have a term which is purely time dependent and divided by k squared. Then I have a term which is purely time dependent and the purely time dependent object divided by k squared. So the dependence in k squared is rather simple. There is constant term plus, well, constant. Time dependent term divided by nothing, time dependent divided by k squared. Now, what I'm going to do, I'm going to study modes for which k is much larger, k divided by a is much larger than h. Okay, so what is this condition? This condition means the following. This condition means I look for energies of my modes which are much larger than the typical background energy scale, which is h. At any time, at h. Okay? So usually what we do by this, it means like this cosine kx, now k become very large, so I'm looking at very fast oscillations. Okay, very energetic modes. Modes which are, we usually say, sub-horizon. Sub-horizon meaning that, so if the energy is very large, its length scale will be very small. Right?
Yeah, frequency will
So very small, much smaller than the typical horizon scale. So we call it subhorizon modes. Why we do this? Because in subhorizon scale, we now have this splitting here. So here I cannot do anything. But here I will say that this objective here will be subdominant with respect to this. So I can try to solve the equation approximately. It's just a way to solve the equation approximately. Nothing else than that. When this is the case, then B will be much larger than E divided by K squared. So I can approximately neglect this because this part is both coefficient for this object here. Okay. On top of that, okay, so the equations of motion will be A divided by K squared, delta rho divided by rho dot. Actually, since now on, let me call delta M to be delta rho divided by rho, okay? Just for simplicity. So this will be delta M dot already dl over delta M. Okay, so this is my Euler-Lagrange equation. Hopefully I put it right. I will get 2. I will get this one equal to dl over that one. Okay? So now this will be A dot, there was K squared, A dot divided by K squared, delta M dot, plus A divided by K squared, delta M double dot, equal to minus can I take 1/2 here? Okay, this is just a redefinition of BAE, okay? So this will be minus B delta M. Does it make sense? Hopefully. Hela, okay. Okay? So this is my Euler-Lagrange equation for delta M. I will get, there was a 2. I just redefined this 1 by 2 because so then I don't get 2, okay? Anyhow, B and E are just the function that were there, no? So once I divide it by half, I will still know how to find that. Okay, so then I get this one, okay? I think this is the equation motion that I get here. Then I do another approximation. I will look for solutions of the kind I omega t. Notice that when I will say that delta M is proportional to e to the I omega t. Now, when I do this I to the omega t, remember that from the beginning I was doing this stereo expansion. I was like I kx. So I'm looking for waves solution. Okay. And I will assume that omega is like, because I have energetic modes, I have also to assume that omega probably will be large. You know, I'm studying for very high k, so I expect that omega will be sourced by k. So if omega is proportional to k or something, omega will also be large.
But here you are taking very small perturbation and
No. So the perturbation is small anyway.
Yeah.
If they are waves, that means they remain small.
Yeah. But the energy would be very high then.
Energy will be, but the amplitude will be small.
Sorry?
The amplitude will be small.
Yeah,
It will be like
yeah.
this one. Okay.
But you consider a very high.
Now, okay, now, of course, if I take Planck energy, then the whole thing will become a black hole. What I mean to say is that typical scale of the universe, for example, today, it's like 1 divided by h naught, 1 divided by h naught. It's really, really large scale. So let's say maybe 10 times or 100 times, not huge, immense energy. So let's say H naught now, it's about, I forgot, 10 to minus 33 electron volt, something like this. This is a ridiculous small energy, actually. So even I take 10 to negative 20 electron volt, which is much, much larger than this one, this is still ridiculous in terms even of the mass of the neutrinos, say.
Okay, so with respect to that, you are taking E upon K square,
Yes.
means much greater than.
Yes.
Okay.
So then, when I have this, then let's see what will happen here. So from this one, I will get minus omega square A divided by K square from this term here. And this, this will get, this will become probably plus I omega A dot divided by K square plus B times delta M equal to 0. I will get this. Okay? Now, you notice that if omega is very large, this term with respect to this will dominate by omega. And if omega is proportional to k, this will be order 1 as this one is order 1. So I can neglect this one. Okay, so when I have this, then my wave has told me that I have omega square is equal to B divided by A K square, where this now is a function of time.
How did you put A dot equal to 0?
No. A dot is equal to 0. No, but what I did is A dot is a function of the background. It's not function of K. So it will be order H. What I'm saying here is that omega is much larger than d over dt, which will give me tangential H term for the background. So this one I expect to be much, much larger than this one. So this one I neglect. It's not A dot. Well, you may say maybe A dot divided by omega is almost a 0.
But the contribution of that term would be negligible with respect to the omega square.
Yes, exactly. Then, as a first approximation, this is solved when this. Okay. Now what we have this, if this is a wave, we have that omega is proportional to k square. Omega square is proportional to k square. But then we have a dispersion relation. And we know that the speed of propagation, this wave, is found when we do this. Probably I had to multiply by A because k divided by A is the physical momentum. So that would be the speed of propagation of that wave. So notice then, because omega is the square root of B divided by A times K, sorry, this one, probably, yes, okay. Yes, I should probably write this one. So probably A square times this one. Okay? Then this object here will be my speed of propagation. Okay? But of course, this implies that this will be this. So if I look for subhorizon modes and I make an approximation they behave as a wave, I get the speed of propagation is this one. And you recognize that this one is p dot divided by rho dot. How do I see that one? Okay, so once more, and we know that the speed of propagation must be positive, because if it's not positive, what happens? This wave, instead of keeping to be wave, will start exponentially growing. If omega is a complex number, you will get I omega t. You will have two solutions, one which is exponentially growing and one which is exponentially decaying. But you have an exponentially growing mode, because omega will be plus or minus I something. So to have CS square positive is a necessary condition for stability. I should say something also, that it's when we say I almost finished, and actually if I finish today, tomorrow I will not have a class. So tomorrow we will have only the exam. 1 hour, 10 questions. Quantized gravity. One I told you now. Okay, that's maybe optional question, okay? All right, so now, don't worry, it's not going to be difficult as I said. Okay. Okay, so then, so let me try to finish today. Okay, maybe I take some extra time. So then tomorrow we are more relaxed. Okay.
5 minutes left.
5 minutes left.
5 minutes gap.
Okay. What that? No, okay. No, you are not anymore the timekeeper. You have no voice now. Okay, so.
He's telling 5 minutes gap.
5 minutes gap. Oh, what? Sorry, what is the 5 minutes gap, actually?
Means interval.
You want to do an interval now? Professor Sami, it's up to you.
Yeah,
Okay. Oh, it seems really needed, actually, by majority. Okay, let's do this 5 minutes break. Okay.